All right, let's talk about this concept known as simple harmonic motion, something that you'll see in your physics class. And the most basic example of this is what we call a mass on a spring. So I've got this mass hanging from a spring here on a ceiling, and if we just let it go, it would fall and that would stretch out the spring and it would bounce back up and bounce back down. And if we ignore friction, this would just keep going forever. So imagine this mass has been let go and it's been bouncing, and we're starting our clock right when it's at this position and it's on its way back up. So it's going to do this. It's going to go up, go back down to its regular equilibrium position. It's going to stretch out. It's going to go back to its original equilibrium position, and it's going to get scrunched up and so forth. Well, look at that. That's a sine wave. So with this mass on a spring, we get sines or cosines, depending on when we start our clock. If we started our clock right here, we would call this a cosine. If I start my clock right here, I would call it a sine. A here is our amplitude, because we're going to have some function that looks like y of t. The position at time t is some a sine of omega t or cosine of omega t. A is this distance from the middle to the top. This distance here is A, and of course that would be the same distance here. The period, the amount of time it takes to go through one complete cycle. So the time from here to here, or from here to here, or from the bottom to the next bottom, we call that the period. And we know how to find period in a trig class. It's 2 pi divided by the number in front of our variable. We call that number now omega instead of b, but it's the same idea. The period is 2 pi over that number. And that will be measured in seconds now. And then we also have this concept called frequency, which is just the reciprocal of the period. If this is measured in seconds per cycle, how long a cycle takes, frequency is how many cycles do you have per second. So let's look at an animation here. So I've got this mass hanging on a spring, and I'm going to let it go up and down. So it's going up and down, and look at the graph. The graph here is measuring how high it is at time t. And look, that looks like a sine wave. Now, we could also, instead of having our mass go up and down, there's nothing wrong with it going left and right. So watch this guy go left and right. So now this will be 0. We start at some maximum, we go backwards to some minimum, and so forth. So we could just as easily be graphing that. That would look like a cosine instead of a sine, because that's starting at some maximum, going down to some minimum, back to a maximum, and so forth. Now, you might see this ball rolling around here, going around the circle. Watch him go around. Notice that at any time, the y value is the same as this guy here. See, it's going up and down with it. And this one's going left and right with it. This is an equivalent representation of simple harmonic motion. We've seen this before. This is if we just measure our x or y values as we rotate around the unit circle. So let's start over. Notice here I'm measuring my x values here. I'm measuring this blue distance here. It started at some maximum. Now it's at 0. I have 0x. Now it's at some minimum back here at -1. Back to 0 and so forth. Instead of measuring the x values, I could have been measuring the y values. So let's get this guy back to 0. So look at the red here. Watch it go up and down. It started at 0, went up, now it's -1, back to 0, and so forth. That's exactly what we were getting here. So a mass on a spring is equivalent to a ball going around a circle, where if the mass is bouncing up and down, we're measuring the vertical distance, the sine value of this angle here. And if our mass on the spring is going back and forth like this, we're measuring the horizontal position or the cosine of the angle. So in this formula there, omega is called the angular speed. It's measured in radians per second. It's measuring how quickly we're going around the circle here. How many radians per second are we traveling around this circle at? That's a good place to stop.